Hello viewers, welcome you all. So in this lecture, I am going to take up the next unit of solid state physics, and the unit is magnetic properties of the matter, right? How matter behaves differently when we apply magnetic field on it, right? So according to that, we have different type of materials: diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, ferrimagnetic, right? So in this lecture, I will cover up some important points related to the magnetic properties of the matter, right? And I will take up those points which can be asked in competitive exams, right? So I am starting with the basics of magnetism. We know very well magnetism in all the matter arise because of the presence of magnetic dipole moments inside the matter, and the magnetic dipole moment inside the matter arise because of the magnetic dipole moment of the atom, right? And the magnetic dipole moment of the atom, you can see here, magnetic dipole moment of the atom, it is represented with direction mu. It is arising because of the two type of the motions of the electron inside the atom. One is its orbital motion around the nucleus, and the other is spin motion, right? We know very well when a charged particle moved in a closed path. You can see here, right? The electron is moving around the nucleus in an orbit. Then this is equivalent to the flow of current in a closed loop, and the closed loop, right, small loops behaves like a magnetic dipole, right? It means the flow of this electron or movement of this electron around the nucleus is equivalent to a magnetic dipole, right, whose magnetic dipole moment is given as a I current into area of the loop. You can see here, and we can say that it is having magnetic dipole moment mu in this direction. And this is what? This is a teeny bar magnet, right, which is again having the same magnetic dipole moment. So we can say that the atom, if the atom has single electron, then it is behaving like a teeny bar magnet. So this is the cause of magnetism in the matter: the orbital motion and spin motion of the electron inside the matter. And inside the matter, we have large number of atoms. So different orientations of the magnetic dipole moment are possible, right? I mean, they can be aligned in the same direction, they can be aligned in the opposite direction, they can be randomly oriented. So according to that, we will get the net magnetic dipole moment of the material, right? But we have to start from the magnetic dipole moment of the single atom, right? So you can see here the ability of the material to get magnetized in the presence of magnetic field is known as a magnetization M, and B is equal to magnetic field induction mu naught H plus M. Mu naught is magnetic permeability, right? H is the intensity of the magnetization, and M is a magnetization, right? So B is equal to mu naught H plus M. Here H is the applied magnetic field, we can say, and M is the induced magnetic dipole moment per unit volume. You can see here, right? M, magnetization, right? Magnetic susceptibility, right? It is the quantitative measure of the extent up to which a material can be magnetized, and mathematically it is represented as zeta is equal to M upon H. M is the induced magnetization and H is the applied magnetization, or we can say applied magnetic field, right? So these are the two important quantities: magnetic field induction and magnetic susceptibility, right? Normally, you know very well, we write B is equal to mu naught H. Why? Because we ignore the induced magnetic dipole moment, magnetization. So when we will go for the different materials, we will look at these two important factors. One is the magnetic field induction V, and the second is a magnetic susceptibility, right? Because these two things will tell us the behavior of the material when it is placed in external magnetic field. Magnetic dipole moment, you can see here, it is the quantity that represents the magnetic strength present in the material and its orientation, right? You can see here, I already explained you. When this magnetic dipole moment, right, mu, it is placed in external magnetic field, it experiences a torque that is represented as this. So you have learned all these things right from your 12th class. But here, the thing that I want to make clear, that the exact cause of the magnetism in all the matter is the magnetic dipole moment of the individual atom. If the individual atom has magnetic dipole moment, then it will behave differently. If it don't have magnetic dipole moment, it will behave differently. If it has magnetic dipole moment, right, and all the magnetic dipole moment of different atoms, they are aligned in a particular direction, behavior is different. But if they are aligned in random direction, behavior is different. So according to that, we make the classification, right? And the quantity that is used for measurement of magnetic dipole moment, that is known as a Bohr magneton. I have already told you about it. cut upon 2m or upon 4 pi m. It is the natural unit for the measurement of magnetic dipole moments of the atoms, right? Now I am coming to the first case, that is diamagnetism. So you have learned right from your 12th class that what is diamagnetism. Diamagnetism is the phenomenon due to which when a material is placed in an external magnetic field, it get weakly repelled, right? Because it get magnetized in a direction opposite to the direction of the applied magnetic field. You can see here, right? It means in this case, the induced magnetic dipole moment, right? It is in a direction opposite to the applied magnetic field. That's why it is getting weakly repelled, right? And this diamagnetism, I want to tell you one thing that I forget here, that in case of an atom, if all the electrons are paired, we know very well when the electrons are paired, their spin magnetic dipole moment and orbital magnetic dipole moment will cancel each other, right? Why? Because the motion of all the electrons are not in the same direction, right? So that's why they will cancel out one another magnetic dipole moment, and the atom as a whole will have zero magnetic dipole moment. But if the atom has unpaired electrons, right, it means the atom will definitely have some magnetic dipole moment, right? So here, in case of diamagnetism, diamagnetism is shown by those materials in which all the electrons are paired. They don't have any unpaired electron, right? It is a non-permanent and very weak magnetism which persists only in the presence of external field. Magnetic susceptibility, now it is very, very important, right? Magnetic susceptibility, what? Zeta is equal to m upon h, right? It is negative, we have to remember it, and its value is minus 10 raised to power minus 6 to minus 10 raised to power minus 5, and it is temperature independent. It has nothing to do with the temperature, whether the temperature is decreased or increased, right? It doesn't depend upon the temperature. So it is very, very important point related to the diamagnetism. Examples, atoms with paired electron. I told you that diamagnetism is shown by those materials which have paired electrons, right? And diamagnetism is associated with the orbital motion of the electrons, right? Because when we apply external magnetic field, the orbital motion of the electrons is disturbed. You can see here change in the orbital motion, right, of the electrons. This magnetic dipole moment that arise inside the material, it arises because of the change in the orbital motion. So this diamagnetism is associated with the orbital motion. Otherwise, diamagnetic materials, very well, they have zero magnetic dipole moment, right? It is temperature independent. Examples, bismuth, silicon, copper, silver, barter, inert gases, right? Air, all these are diamagnetic. Superconductors, I will take up the case of superconductor in the chapter superconductivity. So you can see when H is 0, no magnetic dipole moment is there. But when H is applied, you can see magnetic dipole moment induced in individual atoms in the direction opposite to the applied magnetic field. You can see here all the induced magnetic dipoles, right? So this is the case. I will take up the case of superconductor differently, right? So this is about the diamagnetism, right? Then we have Lenzman theory of diamagnetism that we call as classical theory, right? So this theory again proved that zeta is equal to m upon h, you can see here, and it is negative. That was predicted. The susceptibility is negative and temperature independent. It has nothing to do with the temperature. So this is the mathematical part, but we have to remember only the important results, right? Now quantum theory of diamagnetism, again it proved the same thing, right? That the susceptibility is negative and temperature of independent, temperature independent. Now I am coming to paramagnetism. So now if we look at the atom, I told you that atom can have all the electron paired, but if the electrons are unpaired, in that case the atom will definitely have some magnetic dipole moment, right? Now you know very well that in a material there are large number of atoms, right? So it is not necessary that all the magnetic dipole moments of the atoms are oriented in the same direction. Normally they are oriented in the random direction. So when they are oriented in the random direction, their net magnetic dipole moment is equal to 0 when no magnetic field is applied. You can see here, in paramagnetic substance, the orientation of magnetic dipole in absence of external magnetic field are random, leading to net magnetization no, 0, right? But when we apply external magnetic field, now these dipoles start aligning in the direction of a magnetic field, and we will get a net positive magnetization, means the material will get weakly attracted toward the magnetic field, right? These material exhibit or show small positive magnetization, and also the susceptibility zeta is equal to m upon h, it is also positive, but its value is small, right? These materials are known as paramagnetic material, and it is shown by those materials which have a unpaired electron, right? Again, this effect is non-permanent. I mean, if we remove the magnetic field, the material will get demagnetized. No magnetization will be there. It persists only in the presence of external field, right? Now, magnetic susceptibility is slightly positive, as I told you. Its value is 10 raised to power minus 5 to 10 raised to power minus 3. And the important thing is, it varies inversely with temperature. I mean, zeta directly proportional to 1 upon T, or you can write zeta is equal to C upon T. So it means the susceptibility of the paramagnetic material depend upon the temperature. If we increase the temperature, the susceptibility will decrease, right? And susceptibility was what? The ratio of the induced magnetization upon the applied magnetic field, right? You can see atoms with unpaired electron, I told you, such as aluminum, platinum, manganese, calcium, sodium, right, oxygen, all these are paramagnetic. You can see here what I was saying, atomic magnets in the absence of when H is equal to 0. You can see all of them are randomly oriented, but when we apply the magnetic field, now they are external magnetic field, they align themselves in the direction of a magnetic field, and the material get weakly magnetized, right? So this is the case of paramagnetic materials. Now for the paramagnetic material, again we have Lenzman or classical theory that again explain the Curie's law. Curie law means this law, that zeta is equal to C upon T, or zeta inversely proportional to T, right? You can see here zeta is equal to C upon T, right? Quantum theory again explain the same thing. I am not going into it all. Zeta is equal to C upon T, right? Again, this is the Curie's law. Then I am coming to the ferromagnetism. I told you that the individual atoms must have magnetic dipole moment when they have unpaired electrons. In some materials, right, these individual magnetic dipole moment of the atoms, they align themselves spontaneously, right? I mean, they are not randomly oriented, right? But they align themselves spontaneously, leading to the formation of small magnetized zones inside the material, right? We call these small zones as magnetic domains, right? So then if pic is there, I will show you. Yes, you can see here, right? These you can see what I was saying, that in case of ferromagnetic materials, the individual magnetic dipole moment, you can see here, they are aligned spontaneously, right, in small regions of the materials, right? These small regions are called magnetic domains. They, examiner can ask you what is the size of these domains. So their size is usually from 10 raised to power minus 12 meter cube to 10 raised to power minus 8 meter cube. This is the volume of these small domains, right? And the number of domains present in unit volume, 10 raised to power 15 domains can be there per meter cube. So this is the density of the domains. So I was saying that in case of ferromagnetic materials, what happened actually, the condition, the initial condition is same, that the atom has a permanent magnetic dipole moment, means unpaired electron. But the additional condition is that in the small regions of the material, these magnetic dipole moments are oriented in the same direction, right? And these regions are known as magnetic domains. But when we look at the material as a whole, these domains are again randomly oriented. So the net magnetization is equal to 0, right, in the absence of magnetic field. But when we applied magnetic field, you can see here, these domains get aligned with the external magnetic field, and we will get a very strong magnetization. I means these materials will get strongly attracted by the magnetic field. But when we remove the magnetic field, now the important things is going to happen. If we remove the magnetic field, now these domains which have aligned in the direction of magnetic field, they will not disturbed instantaneously, but they will take some time, right? It means even when the magnetic field, applied magnetic field is equal to 0, we will get some degree of magnetization in that material, right? This is the difference between ferromagnetic and paramagnetic. In paramagnetic, if the external field is removed, they will get zero magnetization. But here, this magnetization will persist for a long time, and it will depend upon the temperature. If I increase the temperature, the thermal disturbance will disturb these domains and the magnetization will vanish, right? And the material will simply get demagnetized. So this is the case of ferromagnetic materials, right? These materials, susceptibility of the magnetic susceptibility of ferromagnetic material such as iron, cobalt, nickel, gadolinium, etc. is of the order of this. You can see it is quite high and it is positive, right? Now the ferromagnetic material follow Curie-West law. We know very well that the paramagnetic material follow Curie's law, zeta is equal to C upon T. What these materials follow Curie-West law, that tell us that zeta directly proportional to 1 upon T minus theta, or in some here you can see T minus 1 upon T minus Tc. Here Tc is known as Curie temperature, or theta, you can say it is Curie temperature, right? So you can see from here, right, that the magnetic susceptibility is dependent on the temperature and this Curie temperature also, which is although a constant, right? So when T, this T is larger than this theta, in that case this term is negative, right? So it means zeta is obviously positive, right? T minus something, T is large and theta is small, then it is a small number, but it is a positive, so zeta is a positive. But if theta becomes less than T becomes less than theta, or T becomes less than Tc, then this term will become negative. So you can see the material will become diamagnetic, but this is not going to happen. Why? Because the value of Tc is very, very small. So for all the normal temperatures and for the all materials, this situation is not going to happen, because the value of theta or Tc is very, very small, right? And the materials simply convert from a ferromagnetic to paramagnetic above the Curie temperature, but they are not going to become diamagnetic, right? So Curie temperature is defined as a temperature above which the ferromagnetic materials becomes paramagnetic, and below which they becomes ferromagnetic, right? So this is Curie-West law, right? Now if we plot a M versus H curve, that is also known as hysteresis loop, right? You can see here, you have learned it in your 12th class. So this is hysteresis loop. Now in hysteresis loop, what we are doing, this is the applied magnetic field and this is the magnetization. So you can see, let's start from here. Point A, initially what we did, we apply the magnetic field, the material start magnetizing, right? And after some time it becomes a constant at this point. Then what I did, then I switched off the magnetic field, right? When I switched off the magnetic field, applied magnetic field, now the magnetization will start decreasing, but it will not follow this path, right? It will follow this path, right? And when the initially suppose we were decreasing the magnetic field, we didn't instantly switch off the field, right? We start decreasing magnetic field, but the magnetization is not following this path, it is following this path. So when the applied magnetic field becomes 0 at this point, you can see still we have a magnetization. That is what I was saying, right? This the residual magnetic field, right? Residual magnetic field present inside the material, or magnetization present in the material, we call it as a retentivity, right? You can see here, it will be written here, right? After attaining saturation magnetization in one direction, when the magnetic field is removed, magnetization will not relax back to 0 magnetization value, but some finite remaining magnetization remain as remnant or residual magnetization. It is we call it as a retentivity in physics, right? Retentivity, residual magnetization. If I want to make this magnetization 0, then I have to apply the magnetic field in the reverse direction. So if I apply the magnetic field in this direction, ultimately this magnetization will become 0 at this point, right? And this magnetic field is called coercivity. It is the magnetic field in the reverse direction that is needed to make the residual magnetization equal to 0. So this is called coercivity. You can see here. It is the measure of the reverse field needed to drive the magnetization to 0, right, after being saturated, right? So this is the retentivity and coercivity, right? So we have to remember these things. And what is hysteresis loop? Now if this cycle is repeated toward this side, right, again same kind of this this type of from here to here, from here to here, then back here, and then again if you go on repeating these cycles, you will get this curve, right? This curve is known as a hysteresis loop, right? Coercive field, and this is a residual magnetization, right? Same is the situation here, right, when you will go through this this side, right? So this is about the ferromagnetic materials, from where question can be asked, right? Again we have West theory or molecular field theory of ferromagnetism. So again it is going to prove the same thing, zeta is equal to C upon T minus theta or T minus Tc, as I told you, right? Then I am going to the anti-ferromagnetism and ferrimagnetism. So now I am coming to the anti-ferromagnetism first, then I will come to the ferrimagnetism. So anti-ferromagnetic materials are special type of materials in which the individual magnetic dipole moments are aligned with each other, but they are aligned in opposite direction. You can see here, right? They are aligned in a opposite direction. This one, this one, this one, this one, and this type of behavior is observed at low temperature, right? When the temperature is low and the external magnetic field is applied, the material try to preserve its order. But as the temperature increase, this anti-parallel alignment start decreasing and the individual dipole start aligning with the direction of a magnetic field. So obviously magnetic susceptibility will increase after some time, right? When we go on increasing the temperature, a particular temperature will be reached at which the this alignment, parallel alignment of the magnetic dipoles will get disturbed and the material will simply become paramagnetic. and the magnetic susceptibility will start decreasing, right, with the rise in temperature, right. That temperature is known as Néel temperature, right. It is written here, Néel temperature, right. It is the temperature above which, right, susceptibility start decreasing and the material becomes paramagnetic, right, from directly from anti-ferromagnetic to paramagnetic. So what is the difference between anti-ferromagnetic and ferromagnetic? Anti-parallel alignment, right. In that case it was a parallel alignment, right. You can see here magnetic dipole with similar moments aligns but alternatively in the opposite direction, right. So the net magnetization is 0, right. Examples are chromium, magnesium oxide, iron oxide, etc., right. In the case of anti-ferromagnetic material, magnetic susceptibility is equal to C upon T plus theta. In case of ferromagnetic, it was T minus theta. This is known as Curie-West law for anti-ferromagnetic materials. We will have a plus here. In that case, it was negative, or I can write zeta is equal to C upon T plus Tc, right. So this is about the anti-ferromagnetic materials. Example we must know. Now ferrimagnetism. Ferrimagnetism is again a class of ferromagnetic material, anti-ferromagnetic materials, where the individual dipoles are oriented anti-parallel, but they are of different magnitude. You can see the magnitude of the magnetic dipoles is different. It is high, it is low, high, low. So it means they are oriented in opposite direction, but they will, when cancel out each other, they will have definitely some magnetization because they will not cancel out each other, right. They are of a different magnitude. You can see here in some ceramic materials, the dipole of the cation may align with the magnetic field, while dipole of other cation may not. These ceramics are called the ferrite. They are explaining it in other terms, but what I am saying is the magnetic dipoles are of a different magnitude, right. Magnetic susceptibility of ferrimagnetics is quite large, right, and it also follow Curie-West law. If we increase the temperature, it will decrease, right. Yeah, you can see here ferrimagnetism is similar to anti-ferromagnetism, right, in that the spin of the different atoms or ion line up anti-parallel. However, the spin do not cancel each other, whatever I said, and there is net spin magnetic dipole moment. Below Tn, Néel temperature, anti-ferromagnetics behaves similar to the ferromagnetics, and just above it, just paramagnetics, right. So this is our examples. You can see here these are the different compounds which are ferrimagnetics. These are known as ferrites, right. Now I am going to the very important comparison table for various type of magnetic materials. You can see here that diamagnetism, right. Example: bismuth, silicon, copper, inert gases. Susceptibility is small, negative, order is given, right. Atoms have no net magnetic dipole moment. This is the variation of magnetization with applied magnetic field, negative, right. This is 1 upon zeta versus T graph, right. And this is, you can be given a graph in any question that you have to identify the which type of material it is. So usually these graphs are given. You can be asked example of a particular material. You can be asked the value of the susceptibility, right. Then paramagnetism. Paramagnetism, aluminium, oxygen, right, manganese, bismuth. Susceptibility is small and positive. Order is given. Atoms are randomly oriented, right. I already explained this is the graph between M and H, right. You can see positive, right. This is 1 upon zeta versus T, right. Similarly, ferromagnetism. Iron, cobalt, nickel, gadolinium, susceptibility is large, greater than 100. Domains are there, right. M versus H graph, and this is a 1 upon zeta versus T graph here. M upon T or 1 upon zeta versus T is here. Two graphs are given, right. Then we have anti-ferromagnetism, same thing. Examples: susceptibility, atoms are oriented in domains, anti-parallel alignment, right. M versus H graph and 1 upon zeta versus T. In some cases, you can be given this graph zeta versus T. So in that case, this graph will get inverted. It will become this type. So don't confuse with that. In that case, it will become this. and again this will be the Néel temperature, right? So the graphs will get inverted. All these graphs will get inverted when we will draw them zeta versus t. But here they have drawn for 1 upon zeta versus t. Similarly, for ferrimagnetism, examples, susceptibility, right? M versus H graph and M versus T, or 1 upon zeta versus T. You can say two graphs are plotted simultaneously, right? So this initially magnetization versus temperature. So at critical temperature, magnetization of the material vanish, and then it follow this relation, right? So these are the different important points that are highlighted in this table. So we have to remember this table, right? So this is all about the different magnetic properties of the material. Usually 1 or 2 questions can be asked from here, and the questions are quite simple if we know all these comparisons, right? So thank you very much.